The first objective is to understand what crystalline solids are and how their particles are arranged. This objective helps explain that crystalline solids have particles arranged in a very orderly, repeating pattern. For example, common salts like sodium chloride has ions arranged in a regular cubic structure, which gives it a fixed shape. The second objective is to identify the different types of crystalline solids based on bonding. This objective focuses on showing how crystalline solids can be classified depending on the forces holding their particles together. For example, diamond is a covalent crystalline solid where carbon atoms are strongly bonded, making it extremely hard. Thirdly, to relate the structure of crystalline solids to their physical properties. This objective explains how the arrangement of particles affects properties like hardness, melting point, and electrical conductivity. For example, metals such as copper conduct electricity well because their crystalline solids allows electrons to move freely.
First of all, solids are one of the three main states of matter. In solid, particles are closely packed and vibrate about fixed positions. Solids are classified into two types, which is crystalline solid and amorphous solid. In this video, we will be focusing more on crystalline solid. So, what is exactly a crystalline solid? Crystalline solid is a solid in which particles like atoms, ions, or molecules are arranged in a regular, repeating and three-dimensional pattern. This orderly arrangement extends throughout the entire crystal, making it one of the hardest elements on Earth.
For the crystalline solids, they include properties such as regularly arranged, it has a long order of arrangement of particles, and it is called as the true solids. This is said because it holds the true properties, and it is also anisotropic, in which this means it has different physical properties that goes on in the different directions. Meanwhile, for the amorphous solids, it has the opposite properties compared to the crystalline solids, and in which this includes irregularly arranged with short order of arrangement of particles. It is also called as the imperfect solids due to the said properties. Lastly, it is isotropic, in which this means it has the same physical properties and moves in the same direction. Now, moving on to the findings, in which there are 4 different types of the crystalline solids. And these 4 types of the crystalline solids, they include the ionic crystalline solid, the metallic crystalline solid, the giant crystalline solid, and the last one, which is the molecular crystalline solid. The first one is the ionic solid crystalline, and we take the NaCl as our example, which the NaCl, they are held together by a strong ionic bonds of Na and Cl that are arranged alternately. Then the properties of the ionic solid crystalline, they include a high melting point, a high boiling point, and it also conducts electricity when dissolved in solvents such as water. Secondly, the metallic solid crystalline, in which we take copper as our example. The copper atoms, they are held together by the metallic bonding, with positive atoms that are surrounding the free-moving electrons. The properties include a high melting and boiling points, and also a good conductor of heat and electricity, and it is also malleable and ductile. The giant solid crystalline, or also called as the covalent crystalline solids, are atoms that are bonded in continuous network by the covalent bonds. For example, we take diamonds, in which it has no discrete molecules, but instead it is a one large crystal. The properties include a very high melting point, it is also insoluble in solvents, and it does not conduct any electricity. But different case for graphite, in which it conducts electricity. And the last one, which is the molecular solid crystalline, in which this consists of small molecules that are held together by the molecular bonds, such as ice. Ice consists of hydrogen atoms in which the hydrogen bonds gives a high melting and low density, which later causes the ice to float in water. The other properties also include the molecule solid, in which it does not conduct any electricity.
Up until now, we have discussed crystalline solids as if they are perfect infinite patterns. However, in the real world, a perfect crystal is actually a theoretical idea, which means it doesn't exist. In practice, all crystals contain imperfections, which we call crystal defects. Now, why do these defects matter? They are not just mistakes, they are actually what give materials their specific properties. For example, the reason certain crystals can conduct electricity or why some metals are stronger than the others is often due to these internal irregularities. Broadly, we can categorize these into two main types based on their chemistry, stoichiometric and non-stoichiometric defects. First, let's look at stoichiometric defects. These are often called intrinsic or thermodynamic defects. In this case, the defect doesn't change the chemical formula of the compound. If your crystal is sodium chloride, for example, the ratio of sodium to chloride stays exactly 1:1, even if some atoms are missing or displaced. The crystal remains chemically pure and electrically neutral. As the temperature rises during the crystallization process, atoms gain energy and are more likely to shift out of position, which is why these are so common. On the other hand, we have non-stoichiometric defects. These are a bit more complex. Here, the ratio of the elements in the crystal actually changes. You will often see this in transition metal oxides like iron oxide. Instead of a perfect ratio, you might have a slight excess of metal or a deficiency of oxygen. This happens because some metals can have more than one oxidation state, allowing the lattice to stay electrically balanced even when the atom count is off. Stoichiometric imperfections are best exemplified by Schottky and Frenkel defects. A Schottky defect occurs when a stoichiometric number of cations and anions are missing from the lattice. This creates vacancies that lead to a measurable decrease in the crystal's density, which means it is lighter than it should be. This is commonly observed in highly ionic compounds, where cations and anions are of similar size, such as sodium chloride. In contrast, a Frenkel defect, also known as a dislocation defect, occurs when an ion, typically the smaller cation, is displaced from its original lattice site into an interstitial position. Because the total number of ions within the lattice remains constant, the density of the solid is unaffected. This defect is prevalent in compounds with significant size difference between ions, such as silver chloride or zinc sulfide. That brings us to the end. To wrap things up, the biggest takeaway is that a solid's personality, like how hard it is, or if it can conduct electricity, all comes down to its internal pattern. Whether it's the salt on your table, copper in your wiring, a diamond, or simply a block of ice, the particular bonds therein are what distinguish them from one another. We have reached our goal of connecting these tiny structures to the physical properties we see in the real world. And that's everything from us. We hope this video helped you see chemistry in a new way, from the salt in your kitchen to the wires in your phone.
If you have any question about these solids, or if there's a part you'd like us to explain more, please drop a comment below. We would love to hear your thoughts and keep the conversations going. Don't forget to give this video a like if you found it helpful, and thank you for watching our presentation.